Dear students, welcome to lecture number 15. In this lecture, we will be going to design a doubly reinforced beam. Earlier in lecture number 12, we have discussed what are the various aspects of doubly reinforced beam when we require to design a beam not as a singly reinforced but doubly reinforced beam. So what are the various requirements or conditions when we have to go for the doubly reinforced beam? You can refer lecture number 12 again. Now today let us start with lecture number 15. Here we will be going into detail a design problem where we will be discussing how to do a design of a doubly reinforced beam, that is doubly reinforced RCC beam as per limit state design methodology in accordance with the specification, accordance with the guidelines as well as recommendations of IS 456 2015. So first of all, let us go through the statement part. That means what is the exactly statement and what information is available here. Now you can go through the design statement. That means problem statement. What it indicates that design is simply supported rectangular RCC beam. So first of all, information is available that it is a simply supported beam which you are going to design, having a clear span of 6.5 meter, subjected to a UDL uniformly distributed load of 35 kilonewton per meter. So you can see here the UDL which is given on the beam is a quite heavy type of load is here. What we have to calculate? We have to calculate the required reinforcement and we have to assume the breadth of beam as 300 millimeter and the effective cover is also given, effective cover for compression as well as tension reinforcement as 50 mm. Further, we can assume that beam is supported by load-bearing masonry bars of thickness 230 millimeter. So that means width of the support is given 230 millimeter. And further, it is also mentioned here that we have to use M25 grade of concrete and steel of higher grade, that is Fe 415. So this much information is available in the design statement. So let us start with the solution part. So very first step here we will be taking, first of all we have to select the grade of concrete and steel. So since in this particular design problem grade of concrete as grade of steel is already given, so we will be just taking this information from the problem statement itself. So here we have written that given in the statement of problem, first is width of the masonry support. So support, width of the support is given to 30 millimeter. And further, grade of concrete which we are going to use in this design problem, that is M25 grade of concrete is given, and effective cover for both tension as well as compression reinforcement is taken as 50 mm. You can just go through the lecture number 12 and you will be able to understand that what is the meaning of this effective cover for tension as well as compression. So that means D dash as well as D we have to take that it is equal to 50. We will take it equal to 50 mm. Now we can just close this first step by writing that adopting M25 grade of concrete and steel bars of HYSD, high strength steel we can use here, that is Fe 415. This is the grade. So this much information we have collected from the statement itself. So nothing data is missing. So we need not to assume any information here in step number 1. So another thing which the design of section is in accordance to provision mentioned in IS 456 as simply supported beam with tension as well as compression steel. So we are going to design this beam in which we will be providing steel in the tension as well as in the compression zone. So that means steel will be taking compressive stresses as well as tensile stresses along with the concrete section taking compressive stresses. So now step number 2. Here we have to fix the dimensions of the section where grade of steel is given. So first of all, let us assume that width of beam. Now width of beam, it is already mentioned, so that's why we are writing it as in the first trial, or it is a, or that means it is a restriction that you have to take width of the beam as 300 millimeter. So depth we have to decide, width is given. Now here we have to consider the guidelines in the IS 456. Since the span of beam is lesser than 10 meter, then we can get the L by D ratio by considering the deflection criteria that will be equal to 20. That is for a simply supported case of a beam. So by taking L by D is equal to 20, we get that depth required is 325 millimeter. So you have to just keep in mind that this is the minimum value required. You can go for the higher value, uh, then it will be automatically taking care of the deflection criteria. So for we are providing here D 450 mm, but that will be the reason because you know that load is quite high. So that means UDL is given 35. So this, it is considered a very heavy load. So that's why we have already assumed depth higher depth we will be taking, not 350 like that. We will be taking effective depth is equal to 450 millimeter. So I have mentioned here also that higher depth is chosen keeping in consideration that the uniformly distributed load on the beam is 35 kilonewton, which is quite a heavier load. So otherwise, if this load was just a 5 kilonewton per meter or up to 10 kilonewton per meter, then you can go for depth of effective depth of section is equal to 350 approximately. But since this we can easily presume, and based on the experience we can just easily guess that if we are going to adopt 350 mm, then later on in the deflection criteria it will be getting failed. So here we are just considering higher value of the effective depth. So that's why we are providing here effective depth is equal to 450 millimeters. And another thing which we are adopting here, just for simplicity, and we can take 20 mm diabar, or later on we can just increase as per the requirement. So first of all, as a trial, first trial we can say we are adopting 20 mm diabars as tension as well as compression reinforcement, and 8 mm dia bar will be taken for shear reinforcement, that is in case of when we have to provide the stirrups. So from this information which we have taken, effective depth is 450, and another thing, this effective cover is already given in the statement, that is 50 mm. So you can go through the statement. Here it is given effective cover for both compression and tension reinforcement is 50. So that's why overall depth will work out to be 500 millimeter. So we can adopt overall depth is equal to 500 millimeters and effective depth is equal to 450 millimeters. Now another step number 3, where we have to just evaluate what is the effective span length. That means effective span length L effective, which we have to calculate. And even in earlier design problem of singly reinforced section, we have taken this effective span length based on the IS 456 guidelines. So there will be two type of choices. and we have to take the least value. So effective span, very first condition is effective span is equal to the clear span length plus effective depth of the section. So clear span was 6.5 and effective depth which we had taken 450 millimeter. So it comes out to be 6.95. And the second we have to take the distance between center to center of the two supports. So center to center two support we can take, that is it can be taken by adding clear span plus the width of the support. Width of the support is already mentioned in the design problem that it is 230 millimeter. So it work out to be 6.73. So we are adopting here L effective is equal to 6.73 millimeter. Now step number 4, where we have to calculate what are the various loads and what will be the bending moment as well as shear force based on these loads. So as I have already told you that it is uniformly distributed, that means this much imposed load is already given. So very first step is we have to calculate the self weight of the beam as per the assumed dimensions which we have adopted per meter length. So we can say that W dead load or self weight, that is equal to uh, for each meter 0.5 is the overall depth of the section, 0.3 is the width of the section, and 25 is the unit weight of the RCC. So it come out to be 3.75 kilonewton per meter. Even here we have just written that it is already assumed that finishes, if any, is already included in this value. But in general, in case of a beam, if you are using steel type of shuttering, no finishing work is required. But still, if there is any provision for the finishing work, then we are just assuming that it is already considered in this value. Now dead load and live load on beam. So uniformly distributed load mentioned in statement, let us assuming that it is live load. Live load is included. If there is some dead load in this 35, that is also under consideration we have taken. So that's why we have written here dead plus live load on beam. Even the statement is silent about whether it is a dead load or whether it is a live load. So mostly in the problems we will be considering it as superimposed load, but it is not mentioned. So we are considering if some dead load may be considered in this statement. So that's why uniformly distributed loaded dead load plus live load on the beam, and we have written as WD2 D2. Here it was WD1 and WD2. It is 35 kilonewton per meter. So we are able to work out here that what is the total load, that is WD. Total load is the sum of 35 plus 3.75. So when you add the, you will get 38.75 kilonewton per meter. Now we have to take a partial safety factor into consideration because it is a method of limit state design. So total design load, no, that is the factor design load, we can say when we are multiplying this dead load which we have already calculated, that is total dead load, into partial safety factor for load, that is 1.5. So it is 58.125 kilonewton per meter. You can just compare this value of the dead load, factor dead load, with the initial earlier problem of single reinforced. So it is quite high value. Now for a simply spotted beam, we know that how to calculate the maximum bending moment, which is at the mid of the span, and the formula is WD L effective square by 8. So by this formula we have calculated, and its value is worked out to be equal to 330 kilonewton meter. So this is factored ultimate bending moment for which we have to design this beam. We have to decide the section accordingly, and we have to design the reinforcement which can take care of all this bending moment. So similarly, we can work out factored shear force. It comes out to be 196 kilonewton. It is also a quite high value. Now step number 5, where we have to just evaluate what is the limiting neutral axis depth. So limiting the depth of neutral axis to limiting depth of neutral axis. So that means here we can say that we are just limiting the neutral axis depth. So we are writing it as xu will be replaced, or xu is equal to xu max. So xu max, the formula is 0.479 into d. So it comes out to be 215.55 millimeter. So you can just see here we have limited the depth of the neutral axis to the maximum value, that is limited depth. Now step number 6, if we go through, here we have to calculate limiting moment of a resistance. Now you should be very clear here that in step number 6 what we are calculating, limiting moment of a resistance if it is a singly reinforced section. That means what is the maximum or limiting moment of resistance if this beam is to be designed as a singly reinforced. That means if you are just designing a beam having overall depth of 500 and width is equal to 300 mm, and you are providing only singly reinforced. So what is the limiting moment of resistance if we are going to design this as a singly reinforced? So we can just use this formula 0.138 FCKBT square. So 0.138 and FCK is 25 because it is M25 grade, and width of the section we have taken 300, and depth of effective depth of the section we have just adopted, that is 450 mm square. So after doing the calculation you will be getting mu limited is equal to 209.58 kilonewton meter. Now here you must be clear that what is the meaning of mu limited here. That means if you are designing this beam having whatever the dimension we have taken as a singly reinforced, then its maximum or ultimate movement carrying capacity will be only 209.58, and we have to just to go through the information which we have the calculation gone through in step number 4, that what will be the maximum factored ultimate bending moment due to the loads. So you can just compare this, that is quite greater than this value. So if you are designing it as a singly reinforced, then this much movement it can take. If the bending moment is more than this mu limited, then you have to go for the doubly reinforced section. But as I have told in the previous step number 4, that ultimate bending moment to be registered by section which we are going to design, that is 330 kilonewton meter. So that means if you design it as a single reinforced, it will be able to take only 209.58 kilonewton meter, and but in our case, since the bending moment, ultimate bending moment is 330 kilonewton meter, so it is greater than this value. So you this is the major reason why we have to go for the doubly reinforced section. So it is very much clear from all this value that mu, that is 330, is greater than mu limited. So this beam section has to be designed as a doubly reinforced section. That means this beam, if designed as singly reinforced, it will not be able to take care of all the loads and the movements which are coming on it. So there is some difference between 330 and 209. So that difference will be termed as excessive bending moment, or we can say additional bending moment, for which we have to switch over the design from singly reinforced to doubly reinforced. So that is that this difference will be mu minus mu limited, and we are saying that it is additional bending moment which will be taken care by the doubly reinforced section. So in a doubly reinforced section, total ultimate bending moment is to be registered as So first of all, let us go through the terminology. What was MU limited, which we have already worked out. So ultimately, MU limited is the movement which is registered by. How it will register it? We are forming a couple and couple of force between AST1, that is the tensile steel, which is below the neutral axis, which we are providing in case of a singly reinforced section, and the concrete section above neutral axis. So that means some of the compressive forces will be taken care by concrete above the neutral axis, and tensile force will be taken care by steel below the neutral axis, that is known as tensile steel. So these two forces, compressive as well as tensile, as we have already discussed in the previous lecture, they will be forming a couple, and that couple will be giving rise to MU limited. So that means it is a singly reinforced section behavior. So you can, that means this much of the part of the bending moment, this much portion of the bending moment will be registered by only this singly reinforced section. Now, then what will be doing for M additional? That means what excess bending, who will be take care of the excess bending moment, which is equal to MU minus MU limited. Now this additional movement is to be registered by another couple, and that couple will be between compression steel, that means compressive force taken by steel on the compression side, and some additional steel AS2 which we have to provide to form a couple based on the steel beam theory. You can go through any source what is the steel beam theory. So what we want to say here, that some portion of the bending moment will be taken care by singly reinforced section, and for additional bending moment which remain, that will be taken care by a couple formed by compression steel. So that means you must be aware here that we are providing steel on compression side, but that steel will not be able to create movement of resistance if it is not forming a couple. Then it will be forming a couple with some additional steel. So in compression side we are going to provide steel that is having area ASC, and in tension side we will be providing steel AST1, which we have already aware regarding singly reinforced section, but some additional steel which AST2 we have to provide. So you can say here that on the compression side area of steel will be equal to ASC, but on tension side now area of steel will be AST1 plus AST2. Now you know that MU limited is 209.58. MU ultimate bending moment coming on the beam is 330, and M additional will be 120.42 kilonewton. So this movement, this additional movement is the main issue which we have to handle, and for which we are switching over from singly reinforced to doubly reinforced type of a section. So that means in this type of a design problem, what we have to do, we have to calculate AST1, which is provided as a tensile steel, AS2, which is provided as additional tensile steel, and ASC is the area of steel in compression, which will be taking care of compressive forces. Now let us go through the step number 7. Here we will be able to do the calculation for the area of steel. That means ASC, AST1, AST2, like that. So all the detailed information, detailed calculation regarding area of steel, we will be covering in this step number 7. So first of all, first point is required area of steel AST1, which we have already illustrated. That is, it is just like a singly reinforced section. So limiting percentage of steel corresponding to MU limited, that may be termed as PT limited. That means how much is the limiting percentage of steel which you have to provide so that section may be able to resist ultimate limiting moment of a resistance. So what should be the maximum steel for a singly reinforced section which we can provide? That will be termed as PT limited. Now limiting steel, area of steel limiting, that will be MU limited by this formula. And earlier you may have gone through the singly reinforced design where we were using this formula. We were finding AST, here it was MU. But now it is MU limited, that means maximum bending moment, limiting bending moment, maximum bending moment which a singly reinforced section is allowed to take as per IS 456. So here XU max we have already calculated, and effective depth of the section we have decided. Fy is the yield strength of steel, that is Fe415 grade. MU limited we have already calculated. So after doing the calculation, we are able to get this AST limited is equal to 1611 millimeter square. So this is the maximum steel which we can provide in a singly reinforced section. So you can't go beyond this steel. This is the maximum value of the steel, that means 1611 millimeter square. This much area you can provide as a singly reinforced section, and beyond this you have to find what should be the area of steel which we have to provide in the compression zone. So when we calculate from this area, then PT limited, that means percentage of tensile steel limited, comes out to be 1.193. Now second point is required additional area of steel. Here we have to calculate ASC as well as AST2, and we can take FSC is equal to 0.87 Fy, and FCC already clear that it is the force in the compression steel, that is 0.447 FCK. This is the force in the steel, compressive steel. Here force, I can repeat here that FSC is the force in steel in compression, that is 0.87 Fy, and FCC mean force in the concrete which you have removed to provide the steel, so that is 0.447 FCK. So ASC we can calculate, that is M additional upon FSC minus FCC into this lever arm D minus D dash. That means this is the lever arm between, if we write that this is the ASC and this is AST, and ultimately here what will be the net force, that is FSC minus FCC, and this much distance which will be forming a couple, that is D minus D dash. So okay, so here we are able to work out what should be the ASC required, that means area of steel required in compression zone, that means area of steel which will be able to take the compressive stresses. So after doing the calculation, because M additional we have already calculated 120.42 into 10 raised to power 6, because it was kilonewton meter. So after putting all the values, you will be able to work out that ASC required is 860.46 millimeter square. So this much area of steel you have to provide in the compression side, and this much area of steel you have to provide in the tension side, as in case of singly reinforced. But some additional steel you have to provide AST2, which we are going to calculate, and which will be forming a couple with this ASC steel. So here 860 mm, approximately 860 mm square area is required. So we can provide 3 number of 20 mm dia bar as compression steel, and the area which we have provided, that means area of these 3 number of bars of 20 mm dia ASC, that P is for provided, abbreviation is used. So area of steel in compression which we have provided, that is 942 millimeter square. So this 942 is greater than 860, so it is okay. We can proceed with the design problem. Now how to calculate AST2? This will be taking care of additional moment. Now how it is a couple which we are going to create. So this is 0.87 Fy and D minus D dash. This will be the additional steel which we have to provide so that it can form a couple with ASC, area of steel in compression zone. So these two forces will be forming a couple and they will be creating movement of a resistance, additional movement of a resistance. So this area comes out to be 834 millimeter square. And here that means total area of steel and the tension zone which we have to provide, that AST is equal to AST1 that we have calculated for single reinforced section, and AST2 which we have calculated here, that it is 834 which is required to form the couple. So total area of steel in the tension side which we have to provide, that is 2445 millimeters square. So here, since the area of steel is quite high, we are providing here 28 mm dia bars. Earlier we have assumed 20 mm dia bar, but now we are extending it to 28 mm dia. So we are providing 4 number of 28 mm dia bars, where it will give you area AST that is equal to 2461. So it is again greater than required value. Required was 2445 and provided, which we have provided, you can say it is provided 2461. So it is slightly greater than this. We can provide it in the tension side. So up to this point we are able to find that we have to provide 4 number of bars of 28 mm dia below the neutral axis, that is on the tension side, and 3 number of bars of 20 mm dia above the neutral axis, that is on the compression side, which will be termed as compression steel. Now here another important aspect is we have to check the ductility, whether this much area of steel which we have provided is able to provide the ductility to the section, or whether it is not giving the ductility. So here one check for ductility we can do. Now we have provided, that means how much percentage of steel which we have provided. So this is the percentage of steel provided in the tension side, and this much is the percentage of steel provided in the compression side. So we can use this formula, and this formula, that is the PC limited, percentage of steel in compression limited, that is given by this formula, and putting all the values we are getting this value PC limited is equal to 0.65. Now this is PC limited, and we have PC which we have provided in the, that means percentage of steel in compression side, it is 0.69 and limited value is 0.65. So it's okay, we have provided steel beyond some limited value. This limited value will be giving you the under reinforced section. So that means if your PC which you have provided is less than PC limited, then it will not be under reinforced, it will be over reinforced. So now your section is under reinforced, so this check is also okay. That means it will give you the ductility. That means there will not be sudden type of failure. It will be having a ductile type of a failure, which is recommended by code as a under reinforced section. Now step number 9, here we have to check the deflection. That means how much is the deflection, where the deflection is under the permissible limits. So again, as per clause number 23.2.1, here what we have to do, we have to calculate L by D ratio, that is the maximum value. It should be lesser than this value. This is the LD maximum value, whatever we, 20 was the L by D ratio, and KT and KC are two factors. So KT we can obtain, these are the reduction factor basically. KT we can obtain from figure number 4. So this will be the figure number 4, that is modification factor we can get, and this modification factor is for tension reinforcement. And how we can calculate it? First of all, we have to find out this value, that is the area of here in the code some error is there. You have to see here, this is the area of a cross section of steel. Okay, it is required. Okay, and the area cross section of steel provided, so it is okay, no issue. So FST we have to work out, and whatever the percentage of steel which we have provided, that is the along x-axis. So based on the percentage of tension steel and based on this Fs value which we have calculated, there are various number of curves. So correspondingly we have to pick the value of modification factor. So later on we will do this. And another factor, that is Kc, you have to obtain it from figure number 5. So this is figure number 5. You can see here, this is the modification factor for compression reinforcement. So in case of singly reinforced, it is not required. In doubly reinforced, because we are providing some steel as compression reinforcement. So here you have to pick the value based on percentage of compression reinforcement which we have provided, and accordingly modification factor you can pick how much is the percentage of compression reinforcement which we have provided. Now actual L by D ratio which we have provided in this design problem, L was 6500 and D we have provided is 450. So actual L by D ratio which we have provided is 14.44. Now we have to check this value, or we have to compare this value with the LD maximum. Now how to calculate KT? First of all, that means we have to refer this figure number 4. Referring figure number 4, PT is the percentage of steel in the tension side which we have calculated in the previous step, that is 1.82, and figure this PC will be used in case of figure number 5. So first of all we are referring figure number 4 to calculate KT, and for KC we will be referring figure number 5. So first of all let us go through figure number 4. Here you can see here Fs value we have to calculate. What is FST? Fs is the maximum limit of the steel in case of tension, that is given by 0.58 Fy. So it is 0.58 Fy and into ratio of area of cross section of steel provided, area of steel required upon area of steel provided. So this area of steel, whatever the area of steel we have required in our design problem, and how much we have provided based on that. So you can see or remember in the previous step, we have the requirement of steel which we have to provide is 2445, but we have provided 2461. So based on the data which we have already discussed in the previous steps, we can take the value, that means area of steel provided in tension side required was 2445 and provided is 2461. So after doing the calculation you are getting FST value 240. So similarly you have to, that means you have to select the curve. So this curve we have to select, this as second curve which belongs to FS 240. Now what was the percentage of steel which we have provided in tension? That is 1.82. So 1.82 will be somewhere here. So this is 1.2, 1.4, 1.6, 1.8. So 1.82, that means somewhere here you can say. So accordingly you have to draw a perpendicular line, and then you have to pick the value from this side. So approximately whatever be the value coming out to be, so it comes out to be approximately 0.85. So it is above 0.8. So that means KT value which we are able to get, that is 0.85. And similarly, based on the percentage of steel, that is PC you have provided in the compression side, that is 0.69. So somewhere it will be between 0.5 and 1. And when you suppose it is 0.69, 0.5 and 0.75 we can say. So somewhere it will be here somewhere. So correspondingly, you can pick the value somewhere here. So let me just erase it to get more clear. Okay. So here, suppose 0.69 we have to do. This is 0.75. 0.69. Suppose it is 0.69, and corresponding you have to pick the value here. So this value will be the modification factor Kc. So we are able to get the value of Kc is equal to 1.13. So up to this point we are here, we have evaluated or calculated what is the value of Kt, what is the value of Kc. Now this value we can put in this equation. So what we are getting by putting in this equation, we are getting this value 19.21. So here L by D maximum should be lesser than this value, and in our case L by D which we have provided is 14.44. So it is lesser than permissible value 19.21. So we can assure here that deflection check is okay. So step number 9 is over. We are able to apply the check for the deflection. Now another very important aspect of this type of problem where heavy type of loading is there, we have to check for the shear stresses. That means whether shear reinforcement is required or not. So again you have to refer clause number 22.6.2, and according to this clause statement, the critical section for shear is at a distance d from the face of support and from distance up to. So this same information is applicable for singly as well as doubly reinforced section. So this information even we have discussed in the singly reinforced type of problem. So we have to calculate shear force at this distance, that means at a critical section. So here loading is 58.125 kilonewton per meter. This was the clear span length 6.5, and shear force which we have calculated, that means reaction at the middle of the support is 196 kilonewton, and this will be the critical section which is at a distance. This is the effective depth of the section, because we have to take distance from the face of support away from up to equal to effective depth of the section. Okay. And the width of the wall, that means support was 0.23, so it is half we are taking here, so it comes out to be 0.565. So that means here we have to find out what is the shear force. This is the critical section. So by applying the theory of structure analysis, we can find out ultimate ultimate shear force at a critical section. So it comes out to be 163.20. So it is again, because loading is quite high, accordingly shear force value is also high. So now as per the IS 456 guideline, let us calculate what is the nominal shear stress. So nominal shear stress tau V work out to be 1.2 Newton per millimeter square. So now we have to find out what is tau C. So based on percentage of steel, and you may remember that there was table number 19, and at a support level how much steel was provided, that was 1.19 which we have provided, and based on that steel value we are able to pick the value of tau C. So as per table number 19, by providing percentage of steel and M25 grade of concrete, we are able to pick the value that tau C comes out to be 0.68 after doing the interpolation. Now you can see here this tau V is quite higher or greater than tau C. So that means one thing is very much clear, we have to provide the shear reinforcement, design shear reinforcement. But here you have to note down that when tau V is greater than tau C, then we have to apply one more check. Tau C we have calculated 0.68 and tau V is 1.2. So tau V is greater than tau C. Design shear reinforcement is necessary. Now important part is this one. another, as per the codal guidelines, we have to find out, we have to check what is the maximum shear stress carrying capacity of the section based on the grade of concrete or grade of steel. So we have to pick the value from table number 20. So maximum shear stress for M25 grade of concrete comes out to be 3.1. So that means one thing is clear, your tau C is lesser than 3.1, as well as your tau B is also lesser than 3.1. So that means if this tau B value was greater than tau C max, then you have to redesign the section, and it will not be sufficient to design the shear reinforcement. You have to redesign the section. But here tau C max is greater than both these values, so we can say that it's okay. We can design the shear reinforcement. That means only designed shear reinforcement is required. We have to design what should be the shear reinforcement. So shear reinforcement is to be designed as per clause 40.4 of IS 456. You can refer the clause guidelines 40.4. Now shear reinforcement shall be provided to carry a shear equal to. Now if you see here, three parts are, one is VUS, another is VU. VU was the ultimate shear force which are coming at which we have calculated at a critical section, and tau C is the maximum capacity of the section which is under consideration, and that is the shear force taking capacity of the concrete itself. And now step by step we go through. The VU is ultimate shear force at critical section. Tau CVD is the shear force carrying capacity of concrete section. And what is VUS? Now that means this much shear stress concrete can carry, concrete section can carry. So something is left, that means, but since tau CVD will be lesser than VU, so remaining shear force which is not registered by section need to be designed, and that's why this value VUS is the shear force for which shear reinforcement need to be designed. So if you compare it with the earlier problem of singly reinforced section in lecture number 14, there we have provided nominal shear reinforcement, because in that problem tau V was lesser than tau C, but here tau V is greater than tau C. So here we have to design the shear reinforcement. In lecture number 14, singly reinforced section, we have not designed the shear reinforcement, but we have provided nominal shear reinforcement. So what is VUS? We can just calculate here. VU was 163.2. Tau C we have calculated is 0.68. Width of the section is 300 mm. Affected depth of section is 450. So after doing the calculation, we are able to find out that VUS means shear force which is to be registered by stirrups, shear reinforcement. This much shear force, 71.4 kilonewton, is the value for which we have to design the shear stirrups. So let us again adopt 8 mm dia, two-legged vertical stirrups as shear reinforcement, and we have to design how much is the spacing is required. So spacing between stirrups we have to decide. Now this guideline or this formula is mentioned in the code very clearly, and here it was VUS was here, that means it was SV was here, so we have just rearranged the equation. So that means SV. Now in this particular equation, Fy, you know that it is the yield strength of the steel. Now what is ASB? ASB is the area of the stirrup. If we are providing one leg, two leg, etc., so area of the stirrup we have to calculate. And VUS we have already calculated, that is the shear force for which shear stirrups need to be designed. And what is SV? SV is the spacing between the stirrups. So we have to calculate from this formula what will be the spacing between the stirrups is required. So by putting all the values which we are available with, we are able to get SB required is 228.64. So this is the spacing which is required between. This is the maximum spacing which we can go for. So because we can't go beyond this spacing, you can reduce the spacing from 228, but you can't increase the spacing beyond this. Otherwise, the section will not be safe in the shear. So again, as per the codal advice, we have to apply a check for maximum spacing which is allowed. So maximum spacing should be least of the following. First one is 0.75D, so it comes out to be 337.5, and the 300, which was the another value. So we have to pick the least of them. So least of them is 300 mm, but this least is greater than this. So even this is not applicable. This value is not applicable. We have to go for the 228. So by rounding off, what we are doing, we will provide shear reinforcement in the form of two-legged 8 mm dia vertical stirrups at a spacing 200 mm center to center throughout the beam. That means we are providing 200 mm center to center spacing, which is lesser than the maximum value required. So it is we can say that the section is safe in shear because more number of rings will be provided as compared to the number of rings required. Now, last step here we have to go for the reinforcement detailing. That means how to show the detailing in the form of a drawing so that the person or the engineer at the execution level at the site can take the guideline from this drawing and accordingly they can execute. So here again we refer. Now here this is the brickwork, that means a brick wall, and a 6500 mm is the clear span between the face of the two walls. That means now you can see here, first of all we have provided steel at the bottom. That is, we have termed it as this steel will be basically AST area of total steel which we have provided. So we have provided 4 number of 28 mm dia bars. So this will be 4 number of 28 mm dia bars, and you can see the section here. 4 number of bars we have provided. These are the main steel bars in the tension zone. 300 mm is the width of the section. 500 mm is the overall depth of the section. 450 mm will be the effective depth, because this 50 effective cover is already given, as well as cover to the compression steel is also given. And another thing, steel which we have provided in the top side, that means on the compression side, so that steel is 3 bars of 20 mm dia which we have provided. So 3 number of bars 20 mm dia we have provided in the compression side, and 4 number of bars of 28 mm dia we have provided on the tension side. So this will be the compression steel and this will be the tension steel. And now at last we have provided stirrups. So what was the stirrups? Stirrup which we provide 2-legged 8 mm dia at a spacing 200 mm center to center. So this red color bars which you can see here, these rings, these are the vertical rings. So it is vertical type of shear stirrups which we have provided. 2 legs already we have discussed in the singly reinforced section also. Here this spacing between two stirrups is 200 mm. So this is the way how we have to design a doubly reinforced section. Now you can see here overall depth required is also high, and compression steel as well as tension steel which we have provided. Thank you.